the next section. The topic is rank of the matrix. So in this section we will see the first elementary operation. Then we will see about the row and column equivalence or equivalent matrix. Equivalence of two matrices according to row and column. And the last, echelon form of the matrix, where we use elementary operation row or column, and on the basis of that echelon form we will find the rank of the matrix. Earlier we have seen the definition of the rank of the matrix, and we have solved some problem, some questions to find the rank of the matrix using determinant. So in this section we will use the row operation. So first, see what is the elementary operation. You may be aware about this, so you can skip and you can go to the next topic. So first, what is elementary operation? Suppose we have given m by n matrices, and the ith row of the matrix A, that we denote as a Ri. Then we can define the elementary row operation on the matrix A in different manner, like by interchanging the two rows Ri and Rj. Suppose R1, R2 are two rows, we can interchange R1 to R2 and we can replace R2 by R1. Next, we can multiply by some non-zero element C to any row. Suppose we are taking Ri, so we can write Ri is equals to what? C into Ri. It means we are multiplying Ri by non-zero number, and we can add any two row in the place of one. Suppose we write here addition of one row Ri with another row Rk. It means we are replacing Rk by Ri plus Rk. So in such a manner we can apply the elementary row operation. Similarly, we can define elementary row operation in the form of column. So what we see, in the place of ith column, here we are considering the in the place of ith row we are considering jth column, that is defined as Cj. So what we can do, similar to the row, we can interchange the two columns Cj and Cl. We can multiply any column like Cj by non-zero element. Here we have considered F, and again we can add one column to another to replace the column. So here we have considered Cl is replaced by Cj plus Cl. Now the next point we have to discuss here, that is row or column equivalence. Suppose we have given m cross n matrix that we define in the form of B. If we obtain that B by another m cross n matrix A by a finite number of elementary row or column operation that we have discussed earlier, then B is said to be the row or column equivalent to A. Suppose B is row equivalent to A, then it can be written as in this way: B is row equivalent to A. Similarly, if B is column equivalent to A, then we can write it in that form. So in this way we can define two equivalence, row and column equivalence. So in row equivalence we have to apply row operation, and in the column equivalence we have to apply column operation. Let's take one example. Here we have to prove that A is row equivalent to the unit matrix I3, where the matrix, definitely it should be the 3x3 matrix. So what we have to do here, we have to operate according to row It means using row operation we have to convert A in the form of B. And B is what? It is I3, identity matrix of order 3. So let's see the solution. Here we have given 1 2 1, 3 1 2, 0 1 2 according to row. So what we do here, we replace R2 by R2 minus 3R1, because in the identity matrix if the first element is 1, so in the column rest all should be 0. For that we have taken R2 is what? R2 minus 3R1. So in this case that A21 will be 0. This A21 3 is next, it is 0, and the rest of the element in the second row is according to the operation we have written. Now we replace R2 by R2 plus 6R3. So what we get here, this A22 will be 1. It means the second element in the diagonal form, it will be 1. So how we see it here? This is your A22, second row, second column, it is 1. Next we have to make it 0 in the whole column, so that we write it here R1 is replaced by R1 minus 2R2 according to the second column. Similarly R3 can be written as R3 minus R2. So the both element in the column except diagonal element will be 0. So it is A12 and A32, these two are 0. Now we move to next column, that is the last column. So first what we do here, we replace R3 by minus 1 by 9 R3. It means we multiply R3 by minus of 1 by 9. So in this way what we get, the last element in the third row, third column, A33, it will be 1. In this way we have formulated the diagonal element 1. Now the next part is what? In the third column we have to make it 0 except the diagonal element. So that's why what we do, we replace here R1 by R1 plus 21 R3, and also R2 we replace by what? R2 minus 11 R3. By making this, these two will be 0. This is the I3. So in this way, by this operation, the given matrix A is reduced to I3. So row reduced form we have taken here. Thus A is the equivalence matrix to I3. Now similarly we can define the equivalence of two matrices. Suppose we have given a M cross N matrix B, which can be obtained from the another matrix M cross N matrix A by the finite number of row and column operation, then the matrix B is said to be equivalent to the matrix A. So as we have discussed in the last example, A is the equivalent matrix to I3. Now the most important, that is echelon form. On the basis of that echelon form we will find the rank of a matrix. Here you can see A we have considered M cross N matrix, then matrix A is said to be in echelon form. If first read it, then by matrix we can understand here. If all the non-zero rows precede the zeros rows, if any, another word we can say every row of the matrix which has all its elements 0 occurs below every row which has non-zero element. So which one had the most zeros from the left, it will be in the lower then slide upward, we will take the less number of zeros according to left. So what we see here, the fourth row, it has all 4 zeros, so it is in the last. Now the number of zeros in each row preceding the first non-zero element in that row is greater than the number of such zeros in the preceding row. As we see, in the fourth row it is 0, in the third row 2 is 0, so 1 we have, the last 1 is the greater than all rest. Here also 1 0 we have. So in this way we can have 1 is the proceeding is maximum than the zeros here. And the last, the first non-zero element in each non-zero row, it should be 1. So as you see, in the first, second and third element, third row, the first element, first non-zero element is 1. This is also known as pivot. So in this way we can see this is the equivalent form of a matrix A. It is in the form of equivalent form, where the leading element is 1 in each and every row, and the every element will be 0 in that column below the leading element. Here you can also see the linear independency of the rows. The fourth row is depend on the first 3 row, but first, second and third rows are linearly independent. So later on we will discuss about the what is linearly independent dependent rows. So here definitely you can see these are the leading element 1. It is known as pivot of that matrix. So the number of pivots, non-zero leading element, is the rank of the matrix. So in this example we can see the rank of the matrix A is 3. You can find the determinant of 3 by 3 matrix that include these pivots. It will be non-singular. So you can verify the rank also. Now let's see one example to frame the equivalent form of the matrix. Suppose we have given this rectangular matrix whose first element is 2 1 0 1, second row is 4 2 1 3, and third row is 6 3 4 7. So what we do here, we make the first element of the first row, that is 1. So for that it is 2, it is given here, so just we divide by 2, make it 1. And similarly we can do in the first row. So it becomes what? 1, 1 by 2, 0 and 1 by 2. Now next is what? We have to make 0 below that leading element. So 4 6, at least 4 6 should be 0. For that what we do, R2 minus 4 R1 we take. Naturally 4 minus 4 will be 0, and also R3 is what? R3 minus 6 R1. So 6 minus 6 will be 0. If other elements become 0, that is the later part, but our purpose is here in the first column except 1 we have to make all element 0 which is below the 1. Now you can see when we operate this row operation, in the second row 2 elements are 0, as well as in the third element it is also 0, 2 element also 0. So we go to the next non-zero element in the second row, that is 1, and you can see in the third also it is 4. So what we do now, R3 is equals to R3 minus 4 R2, so that the below to the leading element it should be 0. So our purpose is here the third column, in the third column and third row that is 4, it should be 0. So by doing this, what we see, the total element in the third row is 0. So finally what we see here, only 2 rows are available which has the leading element. That's why the rank of the matrix, given matrix A, is 2. You can also write down here the number of independent rows is 2. So the rank of the matrix is 2. So in this way, if we define the equivalent form of any matrix A, we can also have the rank of the matrix. So the next upcoming topic is canonical form. So after equivalent form, we will go for the canonical form. Thank you for watching this video. Do not forget to subscribe my channel for more videos related to engineering mathematics. So do not forget to subscribe my channel. Keep watching, keep smiling. Thank you for watching this video.